Good afternoon, this is Brandon with Trained by Techs. Today we're going to be demonstrating the difference between running a conventional compression check using a mechanical gauge as compared to a relative compression check. The idea is to show you how much time you're going to have involved doing it the conventional way, well, I'll call it, using a gauge, versus a more intuitive way, a faster way, less invasive way, by means of capturing current through an amp probe or voltage drop across a battery when we're energizing the starter. The idea is, as diagnosticians, we want to gain a diagnostic direction without having the time invested up front. We want to make sure we know which direction we're headed in before we invest any more time than we have to. We're going to begin with a conventional test using a mechanical gauge. The vehicle we're going to be demonstrating on is this 2007 Honda Civic, just because everything's easy to access. Understand, most of you realize that the mechanical test is not going to be easy to perform on every vehicle because there's going to be a lot of time involved. So obviously the first thing we want to do is make sure the engine's prepped properly so we can deliver the right amount of information, we can gather the right amount of information accurately. First we had to warm up the engine, which we've done so previously. Next, because of the location of the fuel injectors, it's best to use a scan tool to disable them through the DLC. But because I don't have access to a scan tool with that capability at the moment, what I'm going to do is come over here and I'm simply going to remove the injector fuse that allows current to flow to the fuel injectors. That'll disable the engine from starting. Next, I'm going to remove all the ignition coils as well as the spark plugs so we can allow the engine to crank over at a decent speed, and because all the spark plugs are removed, it's not going to change cranking cadence. A compression check is not necessarily performed exactly the same way on every single engine. So of course, I recommend you research, just like any service procedure, how to properly carry out the test. When referencing service information, Honda specifies removing all the spark plugs, opening the throttle to allow engine full breathing capability, supplementing the battery with adequate voltage supply to maintain the cranking speed for every cylinder being tested. But one of the key points is that depending on how many times the engine's cranked over, you may give one cylinder over another, a different amount of opportunity to harness and compress the volume of air inside it, to reduce the pressure that we're going to be measuring on the gauge. In the case of this vehicle, service information did not specify how many times to crank the engine over. So we've decided on a set number, and what we're going to do is crank the engine over the same amount of times for each cylinder being tested to keep the testing situation equal for every cylinder. So we've got all the spark plugs removed from the cylinder. We've got our fuel injector fuse removed so the engine will not start. We've affixed the battery charger to maintain battery voltage as we're cranking the engine over, so each cylinder has the same opportunity and the engine speed's maintained throughout the compression test for every cylinder. We're next going to affix a compression hose into the spark plug hole. One of the key points to this test is we still have the Schrader valve in there. What that's going to do is allow the hose to harness the volume from inside the cylinder. When the pressure is generated, it's going to stay behind that Schrader valve and on our gauge. The problem with this test is that if you intermittently have a valve that's not seating, for instance, and you crank the engine over, even with that fault present, whatever volume's trapped behind this Schrader valve is going to register on your gauge as pressure, and it's not going to show that pressure drop. It's very important to know, and that's why this test has limited, it limits your information. It might hinder the test you're trying to perform, what you're trying to divulge from the engine. So we're going to thread this hose into spark plug number 1. spark plug hole number 1. Make sure the hose is seated. Oops. We're going to fix our compression gauge to the coupler. Next, I'm going to go into the vehicle. I'm going to key up and hold the throttle pedal, the APP, to the floor to allow for maximum breathability, no restriction in the intake manifold as far as the engine trying to inhale air. That's going to give each cylinder the maximum capability to produce maximum pressure. I'm going to crank the engine over for 10 cycles. Cylinder 1 with the throttle open appears to be just over 210 psi. We'll go with 212. I'm going to repeat this test on the remaining cylinders. Cylinder number 2 is considerably lower, at just over 190 psi. Honda, in this application, allows for 28 psi variance from cylinder to cylinder. So what was that? Quick math. About 20 psi variance between those two cylinders? A little higher than I like to see. Cylinder 3, about 205 psi. And cylinder 4 just about 210 psi. Excuse me. We're going to reassemble this vehicle, torque our spark plugs to specification, and move on to the relative compression check. So we just completed the conventional compression test on a 2007 Honda Civic with the 1.8 liter 4-cylinder engine. Quite easy to perform, and as you can see, it didn't take too long. If we were to perform that same test on this 3.6 liter, excuse me, Dodge engine, the story's a little bit different. You see, to perform this compression test, we've got to get access to the spark plugs, which sit underneath this intake manifold. Lots of disassembly has to occur just to perform a test, to even determine if the engine has a mechanical fault of any kind. So that's great if we invest the time, and not only did it prove that there was a fault, but the customer wanted to continue through with repair. What if you didn't find a fault? How much time was invested? How much time was wasted? In regards to dollars and cents, how much money of the customers did we invest in just to do a test that only yielded us that there was no engine mechanical fault? So as you can see, to apply that test, the conventional compression test to this vehicle, although it might show you an issue, it might not be the fastest way to determine if there is indeed a mechanical fault at all. So we're back on this V6. Again, the idea of performing a relative compression check over a conventional compression check is our spark plugs are housed underneath this intake manifold. Very inaccessible and requires a lot of disassembly just to perform the test, which may prove that the engine's just fine. So what we're going to do is employ a technique using a Labscope to measure voltage drop across the battery. Now ideally I like to use an amp probe for this. Basically the idea is as a piston approaches top dead center of the compression stroke, puts a tremendous amount of load on the starter, which causes current flow through the starter to temporarily increase. If we can measure the magnetic field around that, current is proportional to the magnetic field. If we can measure that magnetic field and input it to our Labscope, we can in fact determine relative compression when a piston approaches top dead center. The idea is if one cylinder is low on compression, it's going to put less less load on the starter, mechanical load, which would cause less current flow, and it's going to see that reflected in our current trace. Unfortunately today we don't have an amp probe with us, but there's still good news. Voltage drop is directly proportional to current flow. So as more current flows through the starter wire, or in this case the starter circuit, in this case we're going to be measuring the battery cable, more voltage drop is going to occur. If we use our Labscope and we reference battery positive voltage as compared to battery negative voltage, we can measure that voltage drop, and if we AC couple it, we factor out the DC voltage. So let's do that. Let's get our scope prepared to capture this data. So what we're first going to do is go into our scope multimeter. In this case we're using a Snap-on Zeus, but any Labscope capable of 2 traces, actually you don't even need the 2 traces. 1 will show you the data, 2 will allow you to determine which cylinder is at fault, assuming there is one. So we're going to go into our Labscope, and we're going to employ 2 channels here. Now again, the first one is going to be our relative compression trace. What I want to do is I want to set it up for 1 volt instead of, we typically put it on a 20 volt scale because we want to see at minimum 12 volts. If I put it on 1 volt and I AC couple the signal, I'm factoring out the DC. The DC is where the voltage normally rests. If I AC couple, I eliminate the DC, and I'm only going to be looking at the positive and negative changes across that bias voltage. So that's what we desire to see here. So what we're going to do is interface across our battery. Again, we're going to be looking for voltage drop, and because we're AC coupled, it's going to serve as a zoom feature for us. It's going to eliminate that DC, that DC voltage that the AC is riding on, and we're simply going to look at the differences, the variances as each cylinder approaches top dead center compression. That's going to give us our relative compression. What we're also going to do is we research the firing order on this vehicle. The firing order is 1, 2, 3, 4, 5, 6, which is quite easy to memorize. The idea is this. This vehicle, I curtail all my diagnostic approaches to the vehicle I'm working on. And this vehicle, if you look down here, boasts a 2-wire COP ignition system. What that means is it's provided voltage at all times, battery or switched ignition voltage to the coil, and the ground side of the coil is driven by the PCM directly, which is good news for us because that gives us an easy to grab, low-hanging fruit to determine where ignition discharge is going to take place for a particular cylinder. Of course, the ignition is always going to fire real close to top dead center. So what I'm getting at is if we sync a relative compression trace to a particular ignition event and we know the firing order of the engine, it doesn't matter which coil we use. In fact, this is the only accessible coil that's real easy to grab without putting any extra effort into it. So we're going to go right there, and that would be cylinder number 2. This is going to tell us if we do indeed have a dead hole. It's going to tell us which cylinder it is, so long as we know the firing order. So I'm going to grab my pierce probe out of my pocket here. Yes, I pierce wires. I don't have a problem piercing wires. I'm not scared to pierce wires. And yes, I live in the Northeast, which is what we call the salt belt, where salt water gets into these wires and causes a lot of corrosion. And I've never, ever had a problem with this. I don't want to destroy the wire when I pierce it. I simply want to overcome the insulation so the tip of my pierce probe comes in contact with a conductor. That's all I want to do. We researched the wiring diagram previous to working on this vehicle, and my brown wire here provides voltage to the ignition coil. The blue wire is going to be the wire connecting the coil to the PCM, and that's going to be the control wire for the ignition coil, allowing for primary drive of the circuit. I'm going to pierce this blue wire very carefully. Again, I want to overcome the insulation without destroying the wire. That's all I want to do. I'm then going to interface another lead to my scope on channel 2, and the other half of the lead to my control wire for ignition coil number 2. This vehicle boasts a mode of operation called clear flood mode. By turning the key on, depressing the APP, the accelerator pedal position sensor to the floor, request from the PCM that we disable the fuel injectors. That provides us an easy way to test for relative compression. I'm going to do that now. So what I'm going to do now is I'm going to start my buffer. That means the scope is going to start capturing data. I'm going to go in and crank the vehicle over numerous engine cycles. When I come back out, I'm going to stop my buffer, and we're going to use the zoom capability of this scope to bring the data up to a level where it's more easy to analyze. Okay, so our buffer's full. There's nothing on the screen now. So what we're going to have to do is open up our buffer, and you can see where the data is being captured here. You can see the the voltage drop across the battery when our scope's AC coupled on the yellow channel, and the green channel displays every time cylinder number 2 approaches top dead center, because that's where the spark is discharging. Obviously, this is not at a level where we can zoom in and, this is not at a level where we can analyze this data for any kind of difference. So what we're going to do is, we're going to grab our cursor. This is a point of reference where the scope is going to zoom at. I'm going to put it somewhere in the middle of the capture here. And then I'm going to zoom to a more suitable level. And what we're looking for here is, this represents top dead center cylinder number 2. And this represents top dead center number 2. First, I'm going to move this cursor out of the way so it's not impeding upon us showing you what we're trying to show you here. And what I'm looking for is the voltage drop for each cylinder approaching top dead center as compared to the next. What we're looking for is one cylinder not like the other. So what we're doing here is we're zoomed in on this capture to the point where we can see at least one complete engine cycle, and that's what we want to see. I do want to point out, I prefer to view data in more of a trended view so I can see an event occurring over and over again. So if we're looking here, we're seeing one engine cycle. If I had a cylinder that lacked compression significantly to the point where it might be the cause of a misfire or cylinder contribution error, I'd want to see that fault repeat over and over again from cycle to cycle. So in this case, we're past that. We're zoomed in about one engine cycle, and we can see here by way of voltage drop across the battery that the load on this starter is very similar. As this cylinder approaches top dead center to the next cylinder and the next cylinder and the next cylinder. What we're looking for here is a significantly less voltage drop, which would indicate one of the cylinders is not putting a lot of load on the starter as compared to the other ones. And that would point to a potential mechanical fault with that particular cylinder. What I want to point out here is we don't see that significant drop. And could you imagine if we went about testing this vehicle the more conventional way, by removing all the spark plugs and measuring the amount of compression each cylinder can build? All that really tells us is the amount of volume the cylinder can harness and squeeze. If we had an intermittent fault where a valve wasn't seating, it wouldn't be indicated in that capture because the volume of air is trapped behind a Schrader valve. But in this case here in particular, we're not seeing this mechanical fault. What I'm getting at is we would have invested all this time removing the intake manifold to gain access to the spark plugs so we can then remove them and perform a conventional compression check just like we did earlier on the 2007 Honda Civic. The difference is there's no problem here. So we'd have to once again reassemble the engine and bring it back to operating condition and then continue on with our diagnosis. A tremendous amount of wasted time and energy. In some cases money, if we rolled that cost over to our customer because they'd have to approve that compression check. Relative compression check is definitely the way to go to deliver a tremendous amount of information in a relatively short amount of time with little energy invested. And that's our goal here, to increase efficiency and still maintain accuracy. So just to recap on today's test and procedure, we compared a conventional compression check using mechanical gauge and a hose with a Schrader valve on a 2007 Honda Civic, which was very easy to perform that test on, and trying to compare that test being performed on a V6 Chrysler engine where the spark plugs are underneath the intake manifold. We'd have to invest a tremendous amount of time to gain the same amount of information we could get from a relative compression check using a Labscope coupled to an probe, or by way of voltage drop across a battery, which is easy to see when we AC couple the waveform. I hope you gained some knowledge out of this presentation, and we look forward to seeing you next time on Train by Techs. Thanks, have a great day.